Good. Good to have you, Helen.
Thank you.
We'll be in touch. I think there are over 30 some data. Maybe you can start the proceedings.
Okay. Hello, everyone. Welcome to this week's seminar. Our first speaker today is Amirhossein Arzani. He is a tenure-track assistant professor at the University of Utah. He's handling the group. He's handling a group in the Scientific Computing and Image Institute and the Mechanical Engineering Department. He obtained his BSc, MSc, and PhD degrees from Mechanical Engineering from Isfahan University of Technology, Illinois University Institute of Technology, and UC Berkeley. He is the director of the Computational Biomechanics Group at Utah and is a recipient of the NSF Career Award. His research utilizes various computational mechanics and data-driven techniques to study biological flows and soft tissue mechanics. With that, please join me in welcoming Dr. Arzani.
Thank you. Thanks for the kind introduction. So let me share my screen, and it's great to be in this amazing, inspiring group. So, I've been following George well before the pin work. So, he's done some amazing work on cardiovascular fluid mechanics, dissipative particle dynamics, multi-scale modeling, before that on micro nanofluidics. So, George is inspiring well beyond, what we're currently talking about today. So it's great to be here virtually. And so I guess you could see my screen. So I'm going to be talking about how we can use scientific machine learning to study fluid flow near the vessel wall, study either fluid flow or transport in thin boundary layers. So boundary layers are common in various types of flows. Let me bring the chat box so I can monitor the questions too. Okay, great. So we're interested in boundary layers because they happen in different types of fluid flow problems, either biological, environmental, industrial flows. And specifically my group, we're interested in boundary layers in the context of cardiovascular flows. So essentially blood flow or mass transport near the vessel wall. And generally, thin boundary layers are challenging because they could happen because you have turbulence, or you could have thin boundary layers even in the laminar region because you have high Peclet heat or mass transfer problems. And the focus of today's talk will be not on turbulence, but on laminar, high Peclet heat or mass transfer near the wall. So here's an example in the context of blood flow in an aneurysm. So here we have blood flow from top to bottom. It's a two-dimensional idealized expansion of the vessel wall, what we call an aneurysm. And we're solving a mass transfer problem, advection diffusion equation. And we're prescribing a flux boundary condition on the vessel wall. You have zero concentration coming in. And what you can see here, if you solve for this mass transfer problem using finite element, you can see that you have very thin concentration boundaries forming next to the wall. If you want to see structures in the core region, you have to reduce the scale of your color bar to smaller values. And the reason is that the majority of the mass transport is happening in these very, very thin concentration boundaries. So now what I'm going to do now is that first I'm going to talk about the implications of these thin boundaries. Why do we care about them? Motivate the problem and the physics of the problem a little bit. And then I'm going to talk about how we can use physics-informed neural networks or other machine learning techniques to tackle challenges that are involved in thin boundary problems. Okay, so what are the implications of thin boundaries? First, from an experimental measurement point of view, if you want to measure velocity fields near the wall, so this is the momentum boundary layer context, it's a challenging thing to do experimentally. So you could use different techniques. You could use magnetic resonance velocimetry, which in our field, we know it as for the flow MRI. But the issue is that the resolution is really low. You have all sorts of issues. So really, you cannot capture the boundary layer very well. So the velocities that you get near the wall are not really reliable, or the wall shear stress is not really reliable. You can also use particle image velocimetry, which is considered the gold standard in experimental fluid mechanics. But again, PIV is known to have issues in measuring flow near the wall, especially if you have complex geometries. And if you want to measure concentration in these thin barriers, that is even much more challenging. For example, to give you an idea, if you want to use particle tracking velocimetry, the size of the particles that you're using to sample the near wall region is essentially the same order as the thickness of your concentration boundary. So it's really, really challenging problem experimentally. From a flow physics point of view, and I'm interested in flow physics, so that's what my PhD training is in. So that's going to be a focus today. From a flow physics point of view, when you're dealing with these thin concentration bound layers, you essentially what you can do is that you can take a 3D advection diffusion equation. You can think of it as either heat transfer or mass transfer, and you can reduce it to a surface transport problem, okay? Where now, instead of velocity, you're dealing with wall shear stress, which now is playing the role of velocity for you. And it's this simple equation that motivates such dimensionality reduction, that if you take the wall shear stress vector tau, you multiply it by delta n, your normal to the wall distance, you divide by viscosity, you get a first order approximation of the velocity vector near the wall. And since delta n is very small, because we have thin boundary layers, this approximation is very accurate. So now we know that by definition, wall shear stress is tangent to the surface everywhere. So essentially we have a surface transport problem. And we've developed a Lagrangian particle tracking technique where we can track particles confined on the surface based on wall shear stress to study near wall transport. Now, also from a flow physics point of view, what you get is that you can introduce the concept of Lagrangian coherent structures for the wall shear stress vector field to get a feeling about the topology of transport near the wall. So essentially, you can take your time average wall shear stress vector, you could detect the fixed points, essentially the cell type fixed points. You could use techniques from dynamical systems theory to calculate the stable and unstable manifolds, which I call them the attracting wall shear stress LCS, the blue line, and the repelling one, the red line. Now, what are the implications? Well, if you solve a 3D mass transport problem and get the surface concentration patterns, you can see that the hot spots, the red regions you see here, correspond to the blue line up here. They correspond to the attracting wall shear stress LCS. And I'm going to come back to this observation later when I provide some benchmark problems for my Ballular pin framework.
Amir, can I ask a question, please?
Sure.
I think you have the movie actually that you will show that, but
yes.
But these are corresponding instantaneously, and of course they're changing as through the cardiac cycle, right, from systolic peak to diastolic peak, or they remain the same?
That's a very good question. So even though the wall shear stress vector changes in time, it turns out that these LCS are pretty stationary, and the reason that they're stationary, they don't move around in time, even though the fluid flow is unsteady, is that near wall transport is essentially quasi-steady. Because it takes such a long time for particles to move near the wall, they don't feel the unsteadiness around them. They effectively move with the time average near wall velocity. So these topological structures, more or less, for resting state at least, they're steady, even though the velocity vector field is unsteady.
Right, because of the small, yeah, okay, thank you. Yeah.
Sure. Now, if you look at the movie, you can look at this a little bit more closely. So I'm looking at an example of an aneurysm blood flow from top to bottom. I'm showing you a movie of the wall shear stress streamlines. So you can think of this as streamlines of the wall shear stress vector field, or really the velocity vector streamlines near the wall in a very thin bound there. And you see different types of fixed points appearing and disappearing. And these fixed points are not random fixed points. They're related to the flow physics. So for example, if you have a source type fixed point, that's impingement, a sink means upwelling motion, and a cell type fixed point indicates flow separation, which I'm going to be using in my pin benchmark problems later on. So I'll come back to this later. And then these, as I mentioned, there's a nice link between all of this. So these wall shear stress LCS on the wall, they're not random. They come from the interaction of the flow structures away from the wall, how they interact with the wall. So if you calculate the Lagrangian coherent structures on the velocity field, which is what traditionally is done, you get this beautiful vortex ring that hits the vessel wall, and the interaction between this vortex ring and the vessel wall is what determines these coherent structures on the wall shear stress vector field, which in turn determine the surface concentration pattern for your mass transport problem. So you can see the red region in the surface concentration pattern from a 3D mass transport matches the black line here, which is the attracting wall shear stress LCS, which itself depends on the coherent structures away from the wall. So there's the nice link between the physics at different scales. Now, I want to show this work by George 13 years ago. So George has done lots of amazing work on cardiovascular flows, and he's also studied the with, I think, one of your students, in the past, you've studied these fixed points on aneurysms in another context, in the context of flow instability. So that's some amazing work a long time ago. Okay, now another implication of spin bound layers. They're numerically challenging to solve, and this is going to be a big motivation for us here today. So, I mean, if you take an advection diffusion reaction equation, classical equation in numerical solution to PDEs, if you want to solve this PDE using finite element method, it's really challenging. There's lots of challenges, which we discussed in detail in this paper. And effectively, you have to come up with appropriate stabilization schemes. It's high Peter number, it's really difficult. And also a big challenge here is that because of the very, very thin concentration boundary layers, you need to have a very, very fine mesh next to the wall. Just to give you an idea, for example, if the diameter of your vessel is on the order of centimeters, sometimes your next to the wall mesh edge size has got to be a few microns. So that's like a disparity in the scales of the mesh that you have to create to capture the physics next to the wall. So it's really, really challenging to solve with a finite element method. Okay, so for the rest of the talk, I have two goals today. First, broadly, I want to use scientific machine learning to address two things. Number one, improve near-wall fluid flow measurement, because I told you measuring fluid flow or transport near the wall experimentally is challenging. So can we use machine learning to improve that? And number two, I want to talk about how we can use PIN to improve surface concentration calculation in high-vector transport. So that's going to be the next part. So first, let's talk about the first part. And we're going to be using physics-informed neural networks for that. So for this audience, I don't need to go over this. So I'm going to instead focus on formulating the problem. And the problem is this. Let's say you have blood flow in an aneurysm, as I'm showing here. So fluid flow enters here, leaves here, and then you have this sudden enlargement of the artery. Now, let's say you have experimental measurement, and they're sparse. But this experimental measurement is only in the blue region that I'm coloring here. So these measurements are away from the wall. They're not near the wall. However, you're interested in wall shear stress because of all the things I motivated. So you're interested in wall shear stress or measurements in the red region. But you don't have measurements in the red region because you either don't trust the measurements because they're just not so good in the near wall region, or you just don't have them. You have them away from the wall. And also, you don't know the inlet-outlet boundary conditions. You don't have sufficient measurements to quantify that. So you can't use your your forward solver to solve the problem. So the question is that without knowing the boundary conditions, without essentially knowing the flow rate, and with sparse measurements away from the wall, can we project that to the wall to get wall shear stress? And you can see that PIN is a great way to do that. Essentially, what we're doing with PIN is that we are extrapolating or interpolating in this case, not really extrapolating, because we know the velocity at the no slip. So at the wall, the velocity is 0. We have some sparse measurements in the blue region, and we want to extrapolate or interpolate those informations in the red region. And we're going to interpolate not just with regression, but with the physics-informed regression. So that's kind of what we're doing here. Okay, so this is a simple benchmark problem just to see the idea. If you have a 1D advection diffusion transport, you can write this solution analytically as long as you know the boundary conditions. So not that interesting, but if you don't know the boundary conditions, then you can't write this. But let's say instead of the boundary conditions, you have these 3 measurement points, these red crosses in the interior. Essentially, you're replacing the boundary condition with interior condition. Now, this is a perfect example that we could solve PIN and obtain a very good solution without using boundary condition information. Now, there's one challenge here with PIN, and that's if your diffusion coefficient nu becomes sufficiently small. So once the diffusion coefficient becomes sufficiently small, so you go to high-vector transport, it becomes very challenging to solve this with PIN. So that's going to be the next part, and I'll talk about how to address that. Okay, so here's the next example. So let's say you have blood flow in an aneurysm. You have some sparse measurements, these red dots here that you see, and you don't know the flow rate coming into your aneurysm. So you could use PIN, and you could find wall shear stress in the aneurysmal region. And if you compare it with reference CFT simulation here, you can see you get pretty good accuracy. Just one thing to note here is that because this is an ill-posed problem, we're not finding the exact velocity profile at the inlet. It's actually very difficult to do we're finding something different, but essentially it produces the correct dynamics in the region of interest. So you're finding another pattern at the inlet that produces the correct dynamics in the region of interest. So that's not that big of a deal if you're only caring about wall-shear stress in the aneurysm region. Now we've also extended this to 3D problems. So this is a 3D example of this, but here we're only using pressure sensors. We're not using velocity sensors, and this is more recent results. We're still working on this. And the motivation here is that experimentally measuring pressure, especially in vivo directly from the body, is really easy. You use pressure catheter to measure pressure. So now we've used only 2 pressure sensors before and after the stenosis, and we've used PIN to find wall-shear stress, and you can see that the results that PIN gives us here. And there are two challenges we had here that I want to share with this group in solving this problem in 3D. And you have a blocked artery here. So here you have blood flow from left to right. You have a blockage in the artery, so that causes recirculation downstream, which you can see with these wall-shear stress streamlines shown here. So you have this separation in this part. Now, the challenge for solving this problem with PIN in 3D, the two key aspects that allowed us to solve this, one was that very large batch size. So having a very large batch size seems to be necessary when you go to large PIN problems, and that you require a good high memory GPU. And number 2 key thing we had to use to make sure this works is the adaptive activation function. And this is the work of Ameya, which I think I saw was on the call. So thank you, Ameya, for those great works. We've actually implemented all of your different adaptive activation functions. We've compared them all, and they seem to be really, really crucial in making these problems work in more complex settings. And we're hoping to use that in the patient-specific models. We've just started working on patient-specific models right now. Okay, now another thing I want to mention here is that we can also use other machine learning techniques to solve this problem. So PIN is one great approach, but I also want to point out to another approach, another data-driven modeling approach that could also be used to solve similar problems. So to explain that, and this is work done by a master's student who is now at Maryland, let me formulate the problem again in this new context. So let's say you have low resolution experimental data, but it's away from the wall, as I said previously, but you care about the wall, okay? So your experimental data is not only low resolution, but it's also away from your region of interest. Now, you also have a CFD model, a computational model, which has very good spatial resolution, because all the CFD simulations that I show you are based on very, very high resolutions using high performance computing, ultra high resolution. But so minimal numerical error, but you have uncertainty, right? So for example, you don't know the inlet boundary condition, or if you're another source of uncertainty is that if you dealing with diabetes patients, their viscosity is variable often, so you might not know the rheology or the viscosity. So there's some sort of uncertainty in your high resolution, high fidelity numerical method. Okay. Now the idea is that can you combine the two somehow to get improved wall shear stress results or near wall blood flow results. So the idea here is that we're using the classical Kalman filter approach, like a sequential data assimilation method. And the big picture here idea is that if you have experimental data and you have that has error, and then you have a computational model that has uncertainty, as long as you know the distribution of your experimental data error, so you know its distribution, and you also know the distribution, or you can estimate the distribution of the uncertainty error in your CFD model, as long as you know those two, then you can combine them in an optimal way, which the Kalman filter allows you to do that. In an optimal way, you can combine them such that the final model is more accurate with respect to either of the two models. So that's the big picture idea of Kalman filter. In order to do that, you need to write your equations in such a form. So essentially, the computational model has to be written in a linear form, and you also have the experimental measurements to achieve the measurement matrix, which tells you where your measurement points are with respect to your CFD points. And you need to estimate these W and V, which are essentially your uncertainty and error distribution. Now, estimating the error distribution in experimental data and assuming it's Gaussian, that's a big assumption. So I have to first confess to that's a huge assumption, assuming experimental data error is Gaussian and you could estimate that. It's a very difficult thing to do. So that's for another day to discuss. But now, let's say you have your equations in this form. Now, there's really two difficulties here. So you need to have them in this form to really apply the Kalman filter in an easy way. But the problem is that, Navier-Stokes equations are nonlinear. So how can I need a linear matrix A or a linear operator essentially, right? How can I obtain a linear operator from a system that's nonlinear? So that's challenge number one. Challenge number two, the degrees of freedom are huge, right? So just to give you an idea, when we do patient-specific CFD of blood flow, we often have, and we use P2P1 elements. So these are quadratic in velocity, linear in pressure. So if you convert it to an equivalent of a linear tetrahedral elements, it's sometimes on the order of 40 million elements. So it's really, really huge. Lots of degrees of freedoms. So it becomes very difficult to do linear algebra with that. If you use MATLAB to do that, or Python, you run out of memory when you want to do the matrix calculations and everything. It's really, really challenging to work with those, do linear algebra with those huge matrices, even if they're sparse. Now, so the challenge number two is that the matrix A is large. Can we reduce the dimension? Okay, these are the two challenges to do Kalman filter. Now, the idea is that, well, there's something, to use. The idea is to use dynamic mode decomposition because it kind of addresses both of the challenges. It's an optimal linear approximation of your time evolution CFD model. Okay, so that gives us the linear matrix A that we need. And number two, it's a reduced order representation. So you could also reduce the large dimensionality. So you kind of like get both of, solve both of the challenges. Okay, so you could write your system using a linear evolution like this. And what gets me excited, what got me, just a little background about myself, what got me excited about PIN, I'm traditionally not a deep learning person, right? I didn't do any deep learning until my early faculty years, but what got me excited about deep learning was learning about pins, that you can incorporate PDEs in deep learning, because I'm a huge PDE person, I love PDEs. So as soon as I learned, and this was like during the early days, so like late 2019, I think, when I first met Mazir and talked with him about this, it got me excited and it got me into this whole deep learning business, knowing that you can do PDs with deep learning. And what got me interested in DMD a bit earlier than that was the fact that it's a linear dynamical system. And coming from a dynamical systems background during my PhD, this is very exciting because linear dynamical systems, there's textbooks on it. So we know them very, very well. There's lots of geometric interpretations. There's lots of nice things about linear dynamical systems. So that's kind of like what got me excited into PIN and what got me excited a couple of years before that to DMD. Okay, great. Now here's our framework. Okay, so we could combine our low resolution noisy data. So this is how the data looks like. This is experimental data, how it looks. This is, if you compare with CFD, you can kind of get a feeling, observation, get an appreciation about how noisy it is and how low resolution it is. It's kind of like voxelized data. So it represents something similar to what MRI does. And we combine them using this setting. And I have to re-emphasize again that we're not using measurements near the wall because we don't trust them. When you average the voxels near the wall, they have partial volume effect. Part of the voxel is outside of the domain. So it's really, and it's going to be averaging noise within real data. So it's not at all reliable, the voxels at the wall. So we are just discarding the data near the wall. Okay. So now here's how the results look like. So my measurements are noisy, they're low resolution, but they're at the blue region. And I'm applying my Kalman filter approach, and I'm looking at the results in the near wall region. So these errors that you see are calculated based on the red region. So I don't even have experimental data in this region, but the DMD matrix somehow could propagate the information from the outer region. So you can see that plotting error versus time during one heartbeat, one cardiac cycle, you can see that the blue line, the reconstructed data error could reduce the uncertain computational models error. And I don't have experimental error here because I don't even have experimental data in the near wall region. Okay. So now I'm going to go to the last part of my talk, and that's improving surface concentration calculation in high-spectral transport. I talked about how challenging it is to solve mass transport when you have very high Pechet number. So now how can we address that using Pin? Okay, so I'm going to use the singular perturbation theory, and I'm going to next combine that with Pin. So let me very, very briefly motivate the singular perturbation theory. And by the way, this is not new. I think singular perturbation theory has been around for probably close to 100 years or something like that. So it's really, really old school classical mathematics. So let's say you have a differential equation, so something like this. And then you have a parameter epsilon that's very small, and it's multiplying your highest order derivative. Since this is applied to your highest order derivative, we call this singular perturbation theory. So if you want to solve this equation, it's really, really challenging because of this small epsilon that causes singular perturbation. But you might be tempted, like a student might be tempted to just drop this term, right? Epsilon is very small, so let me just ignore the term and solve the equation. If you do that, what's going to happen is that you're reducing the order of your differential equation, so you cannot satisfy your boundary conditions, okay? And it turns out that those boundary conditions is where the boundary layer is happening. So you'll not even capture the boundary. Okay, so that's what's going to happen if you just naively drop epsilon. So what we do in perturbation theory is that we divide the problem in two parts. In the outer region, which is outside the boundary layer, we can safely drop epsilon. So we get a new equation which has no epsilon in it, and it's super easy to solve this equation, right? Simple equation to solve. In the inner region, which is the region inside the boundary layer, the trick is that you define a new variable xc, okay, which is a rescale variable. And that rescale variable allows you to zoom into the boundary layer. If you mathematically rewrite your equation, essentially you've zoomed into the boundary layer, and when you rewrite your equation in terms of xc, this is how the equation looks like. It no longer has that epsilon term multiplied by the highest derivative. So now this becomes much, much, much easier to solve. Okay, so and then you have these two different solutions, you match them at the interface. Okay, so that's kind of like a matching condition at the interface. Okay, now our goal is to replicate this classical mathematical theory with machine learning, and the motivation is that if we do that, now we're going to have a hybrid, and specifically if we do that with Pin, we're going to have a hybrid physics-based and data-driven approach to modeling thin boundary. Okay, so that's the motivation. And that led us to introduce this Ballular Pin Approach, which was recently published in JCP. And essentially what we're doing, and I'm going to explain this, but big picture, what we're doing is that we're replicating the asymptotic expansions and perturbation theory with physics-informed neural networks. Okay, so how are we doing that? So let's say you're solving for u as a function of x. Okay, so you have this boundary there. So your inner region is this green region, the outer region is this red region, and you write your solution in the outer region and inner region as a sum, as a series, as an asymptotic expansion of a bunch of basis functions, phi. So phi are different basis functions, and delta epsilon are just predefined functions of epsilon. Essentially, the simplest form is just epsilon to the power n. Okay. So essentially, the epsilon term is hard-coded. You hard-code that into your framework, and the basis functions phi are what you want to solve. And the more you include, the more accurate your expansion is. So it's essentially the higher order. You have higher order terms, and you can write that for the outer region. You can also write that for the inner region with a separate basis function side. So now, the idea is that we do this. We have two sets of parallel neural networks where each neural network is finding these basis functions as a function of space and time. Okay, so essentially we're using Pin for all of these basis functions in a Pin fashion, I should say. We're writing a neural network in a Pin fashion, meaning x space is input, the variable is output, and we're stacking them in parallel next to each other. So we do that once, a bunch of them for the inner region, a different set for the outer region, and then with back propagation and everything, you could calculate the derivatives. And on a paper, you have to derive these equations. You have to derive on a paper, okay? And then once you derive those equations on a paper, you could incorporate them as your equation loss in this framework. And something that I think is interesting about this is that once you want to form your final solution here, you essentially you take these parallel outputs, this size, and you multiply each of them by a predefined epsilon function, which is kind of like predefined, and you sum them up. And recently reading about DeepNet, I think this is a little bit similar to the last part of DeepNet, where you're essentially doing that dot product of the tensors. And correct me if I'm wrong, where
Amir, I have a question.
Yeah.
Yeah, it is similar to DeepNet. Also, I don't know if you saw the paper by Zogren, who is here, one of the hosts, who did this multi-head, because it seems to me that you could train psi naught to psi synergistically by one body and then have the different heads for each one of them. So we call it the multi-head.
Yeah, I've seen that paper, but I haven't got, I think it came out very recently. I haven't read it yet, but I've seen that.
So that could be a convenient, and sometimes we discover, Zogren, I think you have an opinion, right?
Yeah, I think it could be, the multi-head structure could be applied to this scenario.
Interesting. I should give that a read. Definitely.
We're happy to see that we could use it also here, because we're thinking what kind of uses we have, and there's many uses, but we didn't think about this. Maybe we could look into it.
Yeah, sure. Interesting. Nice. Yeah, great. Well, yeah, so there's a little bit, similarity in this part where you form the final solution to DeepNet, and there's another similarity with DeepNet conceptually, not in a framework, and that's that in this setting, you're incorporating your parameter epsilon analytically. So what that means is that once you train this once, you could change epsilon within the small region, of course, and find a new solution. So you could think of it as a parametric pin, or that somehow gets into the world of DeepNet, but it's effectively doing some sort of, maybe not exactly operator learning, but something similar to that, or parametric learning, where the parameter is not, it's analytically incorporated. So it's hard-coded into the formulation in an analytic fashion. So you could do parametric reevaluation without retraining. So that's another, somehow tangent similarity with DeepNet. Okay, so you do this, you have the inner regions, you have the outer regions, and then you have your equations, you have the equation laws. If you have data, you enforce that on this final formulation for your inner outer. You have a matching boundary condition too. That's another loss. You have a bunch of losses, right? That you somehow add them up together and you find your total loss, define your total loss, and use that to optimize all these parallel networks. Okay, now let's get into some examples. Okay, so here's a 1D example. It's a simple 1D nonlinear differential equation. And if you solve this, so the blue line is the true solution. So it's like a very, very sharp boundary there. And the outer region of BL pin is the pink dashed line, which you can see it's exactly on top of it. And the red dashed line is the inner solution of BL pin, which is exactly on top of the boundary region. And even with X pin, we were not able to solve this appropriately. So you can see that it's kind of confused. The traditional pin solution is confused by it's kind of getting the qualitative trend in the outer region, but because of the boundary condition here that we have, it's kind of gets a little bit confused and gets a little bit shifted, and it cannot make that sharp transition turn. Okay. Now you can also do this in 2D. This is a 2D advection, very, very simple benchmark 2D advection diffusion equation where you have a Cote flow, classical boundary layer stuff. That on top is your reference finite element simulation. This is with high resolution in Phoenix, our favorite open source finite element solver, my lab's favorite open source solver. And if you can do pin, you can do BL pin, and you can see that pin kind of quantitatively it's off, but BL pin can capture this. And you can also do inverse modeling. And by inverse modeling, I mean here that let's say you have some sensors in the boundary region. So these are the gray spheres you see here. They're sparse sensors in your boundary, and you don't know the flux. You're interested in measuring the flux boundary condition in this mass transfer problem, which is equal to -10. You can see the -10 here. So if you do this inverse problem, you can see that pin converges to something like -8, whereas BL pin converges to the correct solution. Okay, so you can also see that somehow it seems to be converging. I just noticed this now a little bit faster, at least in terms of number of epochs. Well, of course, the training cost, you can think of it as being twice because you have if you're only considering one first order, still with just first order, it's twice training class because you have two sets of them. But it seems like it's converging a little bit in terms of epochs at least.
Amir, maybe you said it and I missed it. How many basis functions you keep?
So I had only one example in the paper where I keep two sets of basis functions. So let me go back to here. So all the examples I'm showing here are only first order. All the examples are only first order. I only have one example in the JCP paper that I'm not showing here today, where I keep the second order as well. But the thing is that the second order approximation, I found out that in this setting might not be that useful because this BL pin compared to pin really becomes advantageous when your epsilon is very, very small. If your epsilon is a little bit small, but not that much small, then pin could still do the job. So going for second order approximations in this setting might not be really, you could do it and you could get very good results by keeping the second order term, but pin could already do it. So, and when you go to very, very small epsilon regime, the second order effects, the order of epsilon squared, they become really, really small. So that's kind of like the reason why in most of these benchmark problems we don't have that. But there's an example in the paper where we keep that, where epsilon is not very small, so we could show that difference. Okay, so now we can also do this in another benchmark problem. This is the 2D double gyre problem. So we have two counter-rotating vortices. This is the benchmark problem that people use in studying Lagrangian coherent structures or chaotic advection. If you solve this with FEM, this is the concentration you get. So I'm imposing a flux at the bottom wall. So there's a flux at the bottom wall. This is what FEM gives you. This is what pin gives you, which you can see it's a bit, it's off. This is what the boundary BL pin gives you in the inner region, which is actually pretty good. And I'm plotting it quantitatively here so you can see how well it exactly matches the reference solution. However, if you look at the BL pin in the outer region, even though it's qualitatively much better than pin, still quantitatively it's off. And the reason is that we're not doing anything special in the outer region. In the outer region, there's nothing special going on. You still have to deal with the challenges of solving high-Peclet mass transport. So you still got to deal with that. There's nothing special going on in the outer region. So therefore, we still cannot tackle that issue. And I should tell you that even with finite elements, that's kind of fair, I think, because even with finite elements, it's challenging to solve these problems in the outer region even. You need stabilization, or you need very, very high resolution, either very, very high resolution mesh or stabilization, all sorts of stuff. So it's really not that fair to be making the direct comparison with FEM here. But I want you to be aware of that issue. So that perhaps could be solved with more like domain decomposition. I'm seeing there's a new adaptive domain decomposition approach that we've also been implementing with that for our 3D problems. It seems to be helping a lot. So, perhaps newer developments in PIN could help tackle that issue. But I think it's a fair thing to say because even with FEM, it's super challenging to handle that, the high-Peclet transport. Okay, you can also do another test case. This is the 3D Berger's vortex, where you have the velocity profile written analytic like this. We do high resolution FEM, so 4.6 million elements. And you can see the surface concentration. So we have flux at the bottom of this vortex. And you can see the surface concentration from FEM, from pin, and from BL pin. So you can again see that BL pin significantly, and you can see it quantitatively here better as well, significantly improves the solution. Now, the last benchmark problem I have here is something that I want to make links to what I talked about earlier in the flow physics part. And this is a full 3D problem. So this is completely 3D. It's a 3D advection diffusion equation. And we're interested in studying mass transport in this one near a flow separation profile. Okay, so near a flow separation region. So now to cook up a neat benchmark problem. So we want all of these to be benchmark problems. So to create a very nice benchmark problem for flow separation, what we did was that we use these definitions that I already talked about, that you can write velocity near the wall. And if you know Wall shear stress, you can write velocity near the wall. This is the tangential approximation, which is just the scale of Wall shear stress. The normal velocity near the wall is essentially proportional to the divergence of Wall shear stress and its second order effect. So Z is the normal to the wall distance. Okay. So we are assuming the coordinate system, the wall is Z equals 0 in the coordinate system. Okay, so you can write velocity near the wall once you know Wall shear stress. So now, if you remember, I earlier told you that a saddle type fixed point in Wall shear stress corresponds to flow separation. So what you can do if you want to create like a neat analytical benchmark problem, you can write analytically a Wallis stress vector field. And this is 2D because I'm looking at the wall. So at the bottom, even though the full problem is 3D, the wall where I'm defining Wallis stress is 2D. So this is, if you linearize this and calculate eigenvalues and everything, you can show that this is a cell type fixed point. You have a cell type fixed point here. So once you define this vector field, you could analytically write the velocity in terms of that in the tangential direction, so the xy component of velocity near the wall, and the normal component, so the z component of velocity near the wall. So we have an analytical representation of a neat benchmark analytical representation of velocity, which we can plug into these equations and solve for concentration in 3D. So we did that with finite element using high resolution simulations in Phoenix. That's what you see here. I'm plotting the surface concentration, and I have a flux imposed on that wall. And remember, I'm interested in surface concentration. I'm interested in transport near the no-slip wall. So that's what the concentration pattern looks like for the reference FEM simulation. And by the way, I talk about concentration, but all these things you can think of it as temperature as well. You can think of it as convection, diffusion, heat transfer. So all these things could translate to high parental heat transfer problems too. Even in lower parental, we've done some investigation, it still holds. Many of these flow physics aspects at least holds even in lower parental numbers. Anyway, this is the reference FEM simulation. This is what pin gives you. So you can see, it's kind of missing the thing. BL pin is what this gives, what you get here, which you can see it's, much better than pin, and you can see a bit more quantitatively here as well. So you can see it's not 100% perfect, but it's pretty good, and at least much better than pin. And something interesting that here we observed was that, earlier I told you when I talked about the flow physics that you could ignore the transport away from the wall in these types of mass transport problems. You could reduce the 3D mass transport to a surface transport. I already talked about that. So here we were motivated by that. So can we do the same thing here? Meaning that I ignore the outer pin network. I only consider the inner pin network. So I only do BLP with the inner region. And at the interface condition, I simply put 0 as my matching condition. So I ignore the outer region. So if you do that, this is what you get. So you could, and this is not surprising because we've extensively studied this problem with finite element and particle tracking in the past, that you could make this reduction of a 3D transport in this kind of cases to a surface transport. So we can do that same thing with pin. Okay. Now, another interesting observation here is that the region of high surface concentration that you can see this line. This is actually not random. This is the unstable manifold of the Wallis stress vector field. So in other words, this is one of the eigenvectors of your linearized vector field around the cell type fixed point, which you call it the unstable manifold in dynamical systems theory, or what I call the attracting Wallis stress LCS. So I'm not showing it here, but there's a line here exactly in the center here. That's the attracting Wallis stress LCS, which essentially what it does is it attracts the chemicals towards itself, and the concentration becomes hot or higher in that region. So there's a correspondence here with the flow physics from the coherent structures in the Wallis stress spectrum. Okay, so now to conclude, we can use pin to quantify near wall flow from either velocity or pressure measurements away from the wall. We can replicate classical mathematical theories with neural networks, and specifically BL pin helps us to study pin boundary layers with a hybrid physics-based data-driven approach. And there are two interesting observations. Number one, the BL pin approach becomes more accurate as you make your viscosity smaller and smaller. And this is exactly opposite to the classical finite element or finite difference numerical methods. If you solve this with classical numerical methods, the smaller the diffusion coefficient becomes, the less accurate your solution gets. But here, because we're using perturbation theory, it's exactly opposite. You become more accurate, actually, as the diffusion coefficient becomes smaller. And the last thing is what I talked about, is that you could automatically reevaluate the solution without retraining for different diffusion coefficients, because it's hard-coded analytically in the equation. So this somehow reminded me of a deponent when I first observed it. Okay, now I'd like to thank my collaborators. These are the collaborators just on the presented work. We collaborated with many more amazing groups, and these are just the funding sources for what I showed you today. And thank you for having me. So if you have any questions, I'll be happy to answer them.
Thank you, Dr. Ahmed. That was amazing talk. Do we have questions?
Since okay, nobody's asking questions, but Amir, did you try to contrast this with self-adaptive weights, for example? So we when we have boundary layers, we always involve self-adaptive weights, which was developed at Texas A&M. You probably know that paper, and most of the time doing very good job. I think
yeah. Okay, I know what you mean. So you're talking about when you make the lambdas, you automatically update the lambdas that where you combine the different loss terms.
So you solve a minimax problem.
Right. Exactly. We've actually implemented
some data.
that.
Yeah, some data is
So
working on it. Lots of people in the group who's working on it, but they're working on it. But the original idea came from Ulysses Braga, Nero Braga.
Yes. So we've implemented that for 3D problems actually. So in this example here that I showed you, we'll use that actually in this example. That the Texas A&M thing that you mentioned. So we've implemented that in this case, but in the BL pin approach, it doesn't help because the issue is not. The issue is a little bit different. It's just the sharpness, the highly nonlinear nature is really what's causing difficulty for pin. But in these 3D problems, we did implement that actually. So that's another thing right next to the adaptive activation.
I think it does help. Varun, who's here, a student engineer, he did extensive studies actually with that. That was his first warm-up exercise to look at boundary layers. Varun, do you have an opinion?
Yes, I think if you play around with the adaptive weight, the learning weight, and all, it might actually be useful in this case as well. I mean, I've not tried anything as complex as this, but the problems that I work with, the self-adaptive weights have been useful in most cases.
So it was very small. I think the viscosity was like 10 to the minus 5 or something, and we have it in the course we're teaching with Raj. We have it actually in the teaching material, but certainly I agree with you in the limit, the perturbation theory, and you're using it synergistically. That's something also that I wanted to congratulate you on, using the applied math to improvise and help pins, because these days even in applied math departments we don't teach perturbation theory anymore.
Wow.
Which was I had to go through a lot of that and in the books of Forzak and so on at MIT, but other people here don't they don't do this type of now they're not teaching this anymore, and it's very useful. This is exactly where you use creatively the mathematics. But it would be interesting to see cases where direct comparison of where the sophisticated self-adaptive weights, and I have another student, Juan, who is working on that with perivascular flows in the brain and artificial, what do we call artificial intelligence and velocimetry, where we really need to be very accurate at the wall, like you're saying. It's something we haven't published yet, but we're after the near wall details, small vortices, and that make these COP modes propel. And he found also a way to improve the self-adaptive weights. And we had also there's another paper called DASA pins, some data. What's the?
Yeah, it's DASA pins. Yes.
DASA pins from my former student who's from China now. They actually have a separate subnetwork to compute these self-adaptive weights. It turns out we're evaluating it now, but it turns out that it's improves the accuracy of self-adaptive weights by a factor of 10 sometimes.
Wow, interesting.
In all benchmark problems, we have maybe some data can point out to the talk that this person, my student gave to Crunch. It's in the YouTube. But these are all, if you have a student I like your benchmarks, benchmark problems a lot. The Tony Perry model that you have is very nice model. That was, of course, he did that for
which one?
No, the next one, this one, yeah. So this was done for Tony Perry, was a celebrated fluid mechanician. I met him many times in Melbourne. We used to hang out at what he called the Institute I was at Princeton at the time. The institute in Melbourne, the Institute of Advanced Studies, was actually a pub across his office.
Okay.
So he would draw this type of for the horseshoe vortices, and he was drawing a model. So this is a model that he has for the advection and separation of the wall of the horseshoe vortices. Really interesting. It is a great benchmark, in my opinion, that I'm glad you included in your paper. We will also follow you on this one, because I think it has some salient features that we'd like to capture in our method.
Thank you.
I also have, if nobody has another question, I have a final question for you, Amir. Which you think that Isfahan is the best university in Iran? Not to put you on the spot.
You have many Persian students on this call. You shouldn't be here. That's a bold claim. That's a bold claim. So I think it's the fourth best. It's the fourth best. But you have to, I mean, one thing about Maziar. So Maziar is not from Isfahan University of Technology. He's from University of Isfahan. So Isfahan has two universities. So I'm from the tech school. Maziar is from the, so the university Maziar is from is more famous for a medical school. They have a famous medical school. So the school that I'm from in Isfahan is engineering school. So
yeah. Ehsan, do you agree with Amir?
Yes, I have to say that I do agree with him.
Okay.
But partially, maybe.
Partially, okay.
you have more students from University of Isfahan?
There's lots of collaborators and students from everywhere, yeah. But I know they teach you good math, and that's great, in addition to engineering, so.
Yeah.
I mean, I shared the link of DASA pins.
Yeah, sure. Thank you. Thanks. I think I've looked at it once before. I'll take a look again. Yeah, thank you.
So we'll move into our second speaker if there are no more questions.
Thank you, Amir.
Thank you.
Thank you, Amir. Our second speaker is a would-be postdoc in our group, Dr. Mario Di Florio. Maybe you would want to share your screen, Mario, while I introduce you. Mario?
Has Mario signed in? He's here? Some
Yeah,
data?
I saw him signed in, but I don't see him now.
Sadhana, is he in the office?
I'll have to check. Just
Maybe the snow has affected him. Okay, he came from Arizona, so.
no, he's not in the office.
Yeah, I just emailed him. Let's wait for a few minutes.
Oh yeah, we're early, 5 minutes early, maybe.
Oh,
You will probably broadcast from the Federal Hill, the Italian neighborhood, where he made lots of friends. as we're waiting, maybe we can have some discussion on the boundary layers. Raj, in the in the course, Raj, are you there?
Yeah, I just called him. He's about to join.
Okay. Because he has done extensive comparisons actually with 1D boundary layers.
Yeah, Mario joined. Hi, Mario.
Oh, hi. Good afternoon, guys.
Afternoon. We actually finished our first talk a little earlier, so we were
Oh,
waiting.
okay. Sorry for being late.
No worries. You may want to share your screen while I introduce you to
Sure.
the audience.
Mhm.
So our second speaker today is Mario Di Florio. He received his bachelor's and master's degree in energy and nuclear engineering from the University of Bologna, Italy, and went to earn his PhD in systems and industrial engineering in 2022 at the University of Arizona. During his PhD studied, he focused on researching remote sensing for meteorites and asteroids and developed his dissertation on the use of physics-informed neural networks and functional interpolation for solving initial value problems. As of February 2023, he would be starting his postdoc at the Crunch Group, but he's already here. So let's welcome him for a holistic picture on physics-informed neural network, extreme machine learning, and theory of functional connections. So you may want to start, Mario.
Thank you very much for the introductions on that. Good afternoon, everyone. And today I'm going to show this brief presentation that is an overview of some methods for solving differential equation involving physics-informed neural network, extreme learning machine, and theory of functional connection. Let's see. Does it work? Yes. I will start briefly with a short overview on how neural networks has been used in the literature to solve differential equation. And subsequently, I will show 4 methods that has been developed in the past 3 or 4 years involving frameworks with physics-informed neural networks and the 2 tools I just mentioned, which is extreme learning machine algorithm and theory of functional connection. And finally, some numerical results of using these methods for solving both ordinary and partial differential equations. So the first time that the physics was used as imposed in the loss function for a neural network can be found in 1992, where basically the goal was of this neural network was to minimize the residuals of differential equation by finding the optimal set of parameters of the neural network. Subsequently, neural networks have been used by tackling labeled data. And in this case, the goal was to minimize the difference between the neural network approximation of the differential equation and the labeled dataset that was coming from observations or synthetic data. Then for the first time in 2019, the physics-informed neural network concept has been formalized. And here the novelty was to embed in the loss function of the neural network both the information coming from the knowledge of the physics that is given by the differential equation and the information from certain data that we can have. And the
Mario, 2017.
Oh, 2017, the first time? I'm sorry, George.
Yeah, the archive was 2017, yeah.
Oh, okay. I will modify it. Thank you. And here the same framework can easily be adapted to solve inverse problems where the goal was to is to discover parameters governing differential equations. Now let's see the first method that we're going to show here. That is the classic physics-informed neural network that most of you guys, I'm pretty sure, know perfectly. Let's imagine that we want to solve a partial differential equation subject to certain initial condition and boundary conditions. So we want to approximate the unknown solution of the differential equation by using a deep neural network. And here the goal, as I mentioned before, is to minimize the loss function that contains both the residuals of the differential equation and the initially boundary conditions. And to minimize this loss function, we need to find the optimal parameters of the neural network by using gradient-based methods, such as backpropagation. And this framework proved to be efficient and robust for many kind of problems in different fields of science. But it has two main limitations, two main drawbacks. And the first one is indeed using the need of using gradient-based methods that are used to train the neural network. And because this often can bring to a high computational effort of the algorithm. And also the other aspect is that in the loss function, we need to embed also the initial boundary conditions. And that needs to be learned by the neural network. And this, of course, will increase the computational effort, and this will lead in a presence of competing objectives in the loss function that will bring to gradient pathologies that can cause the training failure in learning the differential equation constraints. So the first tool that I mentioned before is the extreme learning machine algorithm. Basically, in the extreme learning machine algorithm, we use a single layer neural network where the input weights and bias will be previously randomly selected before the training of the neural network. So in this case, the only unknown parameters of the neural network to be learned will be the output weights beta. And this can be done by using least square methods or iterative least square methods in the case the differential equations are nonlinear. So by embedding this single layer neural network with the extreme learning machine algorithm in a physics-informed neural network framework, in 2020 has been developed the so-called physics-informed extreme learning machine, or PLM. And thanks to this, we can avoid using gradient-based methods, since, as I mentioned before, we only need least square methods to minimize the loss function. Now I want to introduce the theory of functional connections that has been developed in 2017, which is a functional interpolation technique that is based on the so-called constraint expressions. These constraint expressions are basically mathematical functionals that express all the possible functions, as we can see in the animation on the right, that satisfy a set of constraints, of the problem constraints. The constraint expression has this form, where it's basically the summation of two terms. The first term is a free chosen function, is a user-defined function that max exists on the constraints. And the second term is a term where the constraints of the differential equation are embedded. And so what this means that no matter what free chosen function you will choose, but the constraint expression will always analytically satisfy the constraints of the differential equations. By merging the theory of functional connection with the physics-informed neural network framework, in 2020, this new method named the deep theory of functional connection have been developed. And here, the novelty was using the constraint expression to approximate the unknown solution of the differential equation. And as a free chosen function has been selected a deep layer neural network. So now we can see that in the loss function, the boundary and initial conditions are not present anymore, since they will be analytically satisfied by the constraint expression. So the neural network doesn't need to learn the solution on those boundaries, for example. And so we only need to minimize the loss function that is made by the residuals of the differential equation, and this can be done by back propagation. And so with this framework, we can avoid the second limitation of the classic pin.
Mario, I have a question for you. So
Please.
here you can have the boundary conditions could be arbitrary. In other words, can I have time-dependent boundary conditions, Robin type boundary conditions, for example, and time-dependent?
Yeah,
Have that, no problem?
Yeah, no problem. Theory of functional connection, actually, it didn't stop just from that paper. It's been then a framework that have been developed in the last years by Professor Mortari as his previous students at Texas A&M, and they developed many frameworks for solving different complex geometries, different kind of constraints, integral constraints. They are able to tackle many problems. I'm not sure exactly where the literature arrived, but they have no problem for tackling several kind of constraints.
But time-dependent boundary conditions in particular, they can do it.
Yeah, like initial condition.
No, the boundary conditions would depend on time.
Oh, yeah, they can do it.
Okay.
Yes. Finally, I want to introduce now the extreme theory of functional connections framework, which merge both of the two tools I previously mentioned, the Helm algorithm and the TFC, constraint expression. And the novelty here is using instead, as a free chosen function of the constraint expression, instead of using a deep neural network as the deep TSC framework, we've been used a single layer neural network trained via extreme learning machine algorithm. And thanks to this framework, we are able to avoid both the use of backpropagation and the introduction of the initial boundary condition into the loss function. So here again, we only need to find the output weights of the neural network that minimize this loss via least square methods. Now, let's see some numerical results. Well, let's start with the ordinary differential equation, in particular from the monodimensional steady advection diffusion equation, which has this form subject to two boundary constraints. So this differential equation is monodimensional, linear, steady state, and the sharpness of its solution increases with decreasing of the value of nu, which is the diffusion coefficient. Here on the right, we can just see the hyperparameters used for this simulation for the 4 different methods that I previously introduced. And let's see some numerical results. On the bottom, we can find the test case for nu equal to 1, and we can see the solution is pretty smooth, and all the 4 methods are able to learn the solutions. In particular, we can see that the 2 methods using deep neural network and back propagation, they require really high training times in the order of 10,000, 5,000 seconds, compared with the 2 methods using an extreme learning machine that needs order of milliseconds of training time. And the accuracy are pretty much higher for these 2 methods. Indeed, we can see that the maximum and the average absolute error compared with the analytical solution are in the order of 10 up to minus 15 or 16 versus 10 up to minus 8 or 10 up to minus 7. While decreasing the value of the diffusion coefficient, we can see an increasing in the sharpness of the solution. Still here, all the methods are able to learn the solution with almost the same accuracies as before. For the case of nu equal to 0.01, we start to see that the classic pin is not able to learn the solution. And while the 3 other methods are still able and also efficient in a certain way, since we reach accuracy of in the order of 10 up to minus 8 and 10 up to minus 12 for PLM and XTFC respectively, and increasing the sharpness again in the bottom test case, we can see the first failure also for the deep theory of functional connection framework. Finally, in the last case, we can see here how the solution is pretty sharp at the last points of the boundary. And here all the three methods, but extreme theory of functional connection, fail to learn the solution. And XTFC here is able to achieve errors in the order of 10 up to -3. Now let's see how XTFC can be used to solve the stiff problems. For example, I can introduce this example of how now XTFC with the domain decomposition is able to tackle stiff chemical kinetics problem with long time domains. Let's consider this Belousov-Jabotinsky reaction that is modeled by the systems of stiff differential equations, nonlinear. And here we can see 7 plots for the 7 species of the results of 3 different methods, XTFC in blue, and OD15i and OD15s, which are MATLAB implemented functions aiming to solve stiff problems in yellow and red respectively. And we can see that for each species, OD15s in red started to fail in learning the solution after the first steep change in the solution, after the first jump. And all these results have been obtained with a time step of XTFC pretty large compared to the other, in the order of 0.01 and 0.0001 for the other 2 MATLAB functions. We can see now that XTFC and OD15i are able to represent the solution of the system for all the 40 seconds time range. But we can see a slight delay between the 2 solutions. So what we did, it was increasing the domain, the time domain up to 120 seconds. And we saw that actually OD15i was already starting to fail in learning the solution after the 3rd steep change, while XTFC was continuing to represent the same jump in time. And qualitatively, we can think that it can be a robust framework to tackle these problems. So the following question was how much we can push XTFC for huge time domains to solve this kind of stiff problems. So we extended up to 5,000 seconds. And we can see the plot here for 40 seconds domain, 120 seconds domain for 4 species. And the propagation of these developments in time of the species up to, we zoom in here in the time instant of 4,500. And we can see that even for long times, XTFC was able to still represent the same jumps in the solution for all the species. This has been obtained with a time step of 0.01 seconds with a computational time of around 400 seconds. Now let's see how these methods can tackle partial differential equations. We can start with the monodimensional Burger's equation, time dependent, where on the bottom, I just show the exact solution for different values of nu, because we can see how decreasing the value of nu from 1 on the left to 0.1 on the right, the solution becomes much sharper. And so we expect that will be much more computationally challenging for the methods. We compare this problem between XTFC framework and deep TFC framework. Here on the bottom, we can see the hyperparameters used. XTFC, of course, 1 layer and 600 neurons, while deep TFC used 4 layers with 30 neurons per layer. And let's start talking about the smoother solution for nu equal to 1. XTFC in training time compared with deep TFC, it was much faster and also has accuracy. we can reach order of the mean error in order of 10 up to -7 against 10 up to -4. And then by increasing the sharpness of the solution, so decreasing the value of nu, we can see a drop in accuracy with the XTFC that is not able to capture the sharpness of the solution anymore, still while keeping the same training times. And instead, the deep TFC, even in increasing the sharpness of the solution, it will hold the same accuracy. So in this case, we understand that for smoother solution, XTFC can be much faster and reliable and accurate, but the deep TFC wins for this kind of complexity in the sharpness of the solution.
And Mario, by the way, this viscosity is still very large.
Still very large, yes.
Yeah, the standard benchmark is 0.01 divided by pi.
Exactly.
Yeah, so
yeah, it will be interesting indeed in the future to try to use both methods for even higher sharpness in the problem. The last problem I'm going to show is the two-dimension time-dependent Navier-Stokes equations subject to certain boundary conditions. And again, here we do the comparison between XTFC and deep TFC, using 200 neurons for XTFC with 1 layer and 4 layers with 30 neurons per layer with the deep TFC framework. Here we can do first two kind of comparisons, a qualitative one and a quantitative.
Hi, I'm Kamal here from Brown. I have a small question in the previous slide.
So on the previous?
Yeah. Why in deep TFC, it started the optimizer directly from LBFGS?
Excuse me, can you repeat the question?
The optimizer in deep TFC, it started LBFGS. Why not started with Adam and then?
Oh, because with the has been tried with Adam, but LBFGS was giving the best accuracy for this kind of problem. So I just report the optimizer that gave us the higher accuracy. Okay. Yes. Yeah, okay, but thank you. This works better than the Adam optimizer, at least for this problem. So here we can see the solution of the U velocity for both deep TFC on the bottom and XTFC on the top for 3 different times, 0.01 seconds, 0.1 and 3 seconds. Qualitatively, we can see that the solution of deep TFC is much more stable than the XTFC one. And especially here, it's pretty clear that XTFC is learning the solution, but not in a very accurate way. And we can test quantitatively the numerical solution with the steady Poisson profile given at the x equal to 15 at time 3 seconds. And we can see that both the maximum error and the average error for XTFC are in the order of 10 up to -3 versus deep TFC that gain 1 order of magnitude in accuracy. And that's it with the numerical results. And so what we've seen today is an overview of this PIN framework, in particular how they can be merged. How can 2 important tools as TFC and Helm can be merged to create new frameworks and their performances in different test cases. And in particular, we see that XTFCs can be more effective to capture a sharp solution, at least for ordinary differential equation and stiff systems of ODEs. And it can be good to you for using it for partial differential equation when the solution is smooth. And it is, yes, an accurate and fast framework. But deep TFC can be more reliable for more complex problems in partial differential equations, such as the Navier-Stokes ones. Thank you so much for your attention. And please, if you have any question, feel free to ask.
Thank you, Mario. Questions for the speaker?
Okay, so we, we need
Can I
active
ask it?
participation. Yeah, go ahead, Zogran.
This is Suku here.
Yes, cool, yeah.
So I had a question. Yeah, so Mario, I had a question on the number of, like if you look at XTFC, you just used like a single layer with a certain number of neurons, right?
Yes.
And where you fixed the bias and the weight. So only the output coefficients were varying, right?
Exactly.
And then you use least squares on that.
Exactly. This is what extreme linear machine algorithm has been developed.
Yeah.
Yeah.
Okay, so how did you choose the bias and the weights? You just randomly chose it, or?
Yeah, you can randomly choose it. We used to do it between -1 and 1, but I've read some papers in the literature where they were imposing certain boundaries, lower and upper boundaries for bias, where they proved to achieve better results in better accuracy in their numerical results. But yeah, pretty much you randomly select them.
But I mean, because I was wondering, if you did not choose, if you let the training also find out the bias and the weights, did you try that at all, or?
You mean what do you mean, like training the neural network also to learn?
Yeah, the bias and the weight, so that you keep the approximating functions flexible, right? Because you let the neural network tell you what is the best, support and what is the best location of those functions, right?
Yeah. No, yeah,
because then you.
No, I was saying we never tried to this, but that will be a good.
But then, how is that different? How is that different from standard neural network?
Yeah, we probably wouldn't be that different. Looks like to use like a deep neural network and train.
No, Suku is talking about just a single layer, but that's just a standard
single layer. Yeah. It's just exactly a standard neural network is a single layer.
Yeah, that's definitely not better.
Mm-hmm.
Yeah, because the point is that if you don't, because now you're just using some approximating functions and just using a linear combination of those, right?
Exactly. Yes.
Yeah, but but of course, how do you choose the approximating functions is important, right? One would think in general.
Investigated, yes.
Or the question
anyway, we can talk.
The question is actually more fundamental. Do you have any theoretical guarantees that this is converging? Is there a universal approximation theorem for this construction?
Looks like that there is this convergence, that the convergence is guaranteed. I never investigated too much, but it looks like it has been published by Yuan et al. The convergence theorem for this kind of.
Okay. Yes. All right. Okay. I will look into it. Yeah.
Yes.
This is 2006. So there's a
convergence. The paper, you can find the paper here.
Yeah. I wonder what the assumptions are, but
yes.
Okay. Yeah.
Mm-hmm.
But Mario, have you considered the following case where you? It seems that the XTFC is pretty good for stiff kinetics and ODEs in general.
Yes.
So you could use the a method of lines. So you could implement the method of lines for PDs where you have any discretization scheme for space, but then you advance it using the XTFC because of this point, because you can take large time steps.
Yes, exactly. Yeah.
And I was wondering, has anybody investigated the stability of the XTFC? How much, how big of a time step can you take, and compared to any other, let's say, Rangi-Akuta methods, you did the 10 times the time step, or what is, and the accuracy, of course, the accuracy. Are these issues, the numerical analysis issues of XTFC, have been looked at or not?
No, not yet, because this was just a preliminary test cases where we tested on the domain decomposition for the first time. But further research and investigations still need to be done actually in this field.
Because if you look at this table, you're using 100 times bigger time steps
Yes,
than the ODE solvers.
exactly. But yes, this one is just because we, of course, we cannot compare with an analytical solution because it doesn't exist. So this is just for a qualitative results, let's say. We don't know exactly how accurate we can be with this kind of time steps. Maybe for higher accuracy, we need to still decrease the time step to increase also the robustness and the efficiency of the framework. This is things that still need to be investigated indeed.
Are you familiar with the discrete pins that we had in the paper? The second part of the paper that everybody refers to.
Pins?
Yeah, it's called discrete pins, and we use Rankekuta 500, so 500 stages. Because if you increase the number of stages, which is for free, delta t to the number of stages times 2, that's the order of the error. So if you have even 0.999, right, to 100, that's extremely small. You don't see the error. So we take extremely large time steps. Basically, 99% of the characteristic time scale you can jump.
Oh, that's interesting. Yeah, I definitely need to read it. Thank you very much.
Okay, we're looking for active participants in this seminar. So we want questions for the speakers.
My friends online to do some questions. My colleagues. Nothing.
Can I ask one more question?
Sure.
Okay, so Mario, you mentioned going back to the theory of the connections, right? Can you also do like homogeneous, non-homogeneous boundary conditions with in 2 dimensions, for example? With
I'm pretty sure they already did something like that in the literature. I have to research because as I mentioned before, in the past years they have developed many improvements for this theory.
Okay, I'll take a look. Okay.
Yes.
Thanks.
It's a pretty interesting work that those guys did from Texas A&M.
Yeah.
So if there are no more questions, we come to an end for today's seminar. Just a quick announcement. We have cake in the hall area, in the common area. This is for Elham's leaving ceremony or leaving party. And yeah, please join us over there. And yeah, have a good rest of the day and have a great weekend ahead.
Thank you.
Mario, can we invite Mortari to give a talk here?
Of course, he will love that.
Can you extend an invitation on my behalf, please? Because I basically would like to know all the theory and more like theoretical aspects of it, actually.
Of course, I will do it.
Yeah, thank you.
Thank you.
Bye. Bye, everyone.
Bye.
Bye-bye.